Okay, 7b97z43a, line 22, 7b97z43a, atoms, quantum, qubits, laser atomic dance, swap spin entanglement signals, 5G Wow Seti. There's the alien radio signal there. And, okay, so this one's about keyword research, about an atomic dance in quantum qubits. Laser beams rubidium atoms for a UFO space communication ship found in the WOW data lines 22 formulas begin B to F from A. So there's several videos that are part of this series here. Code signals. Okay, I changed the title. That's what happened. So I'm just making a note that I changed the title. So it goes all the way up to F. Okay, so A to F. So that's all you do is you take 43 and 7b97z43 add A, B, C, D, E, F. And you'll find all the videos. Okay. So the previous video, I was working on this August 21st, 2013. Line 22, 7b97z42, Rubidium, Doppler, Broadening, peak, Spectra, Isotopes, 5G Wow Seti. Subwavelength-diameter optical fiber atom trapping and guiding was what I was looking at, and then I looked at the keyword Rubidium atoms, a bunch of stuff came up, and I created several videos with it. I found this keyword on a blog, www.mpq.mpg.de, and the quotes and diagrams are from a blog. Thousands of atoms swap spin with partners in quantum square dance. NIST Advance is step toward quantum computing with neutral atoms, July 25th, 2007, Research News. I don't need to get the hiccups. I've been fighting off a cold this week, and I'm doing pretty good. At least I can breathe today. Okay, so this is a quantum dance, which I thought was cool because I've never seen it before. Thousands of pairs of rubidium atoms participate in a quantum square dance that may be useful in quantum computers. So this is the future of computers, unless we've already used this technology. I don't know. It's from 2007, so it's a couple of years ago. So credit was Trey Porto, JQI. Gaithersburg, MD, physicists at the Commerce Department's National Institute of Standards and Technology, NIST, have induced thousands of atoms trapped by laser beams to swap spins with partners simultaneously. The repeated exchange is like a quantum version of swinging your partner in a square dance, but lasting a total of just 10 milliseconds, which I don't know how much that is. It's probably less. It was less than 1 second, right? So it's like blink and it's gone. Might someday carry out logic operations in quantum computers, which theoretically could quickly solve certain problems that today's best supercomputers could not solve in years. Interesting. The atomic dance described in the July 26th issue of Nature advances prospects for the use of neutral atoms as quantum bits, qubits, for storing and processing data in quantum computers. Thanks to the peculiarities of quantum mechanics, Nature's rulebook for the smallest particle of matter and light, quantum computers might provide extraordinary power for applications such as breaking today's most widely used encryption codes. Neutral atoms are among about a dozen systems being evaluated around the world as qubits. Their weak interactions with the environment may help to reduce computing errors. Now that would be nice. Led by Nobel laureate William Phillips, the NIST group demonstrated the essential part of a so-called swap operation, in which atom partners exchange their internal spin states. Spin can be visualized as a rotating top pointing up or down. In the binary language of computers, the atoms swap values from 1 spin up and 0 spin down, or vice versa. Unlike classical bits, which would either swap or not, quantum bits can be simultaneously in an unusual state of having swapped and not swapped at the same time. Under these conditions, spin swapping has the effect of entangling the pairs, a quantum phenomenon that links the atoms' properties even when they are physically separated. Entanglement is one of the features that make quantum computers potentially so powerful. This is the first time these spin entangling interactions have been demonstrated between pairs of atoms in an optical lattice, says Trey Porto, one of the authors. Other research groups have entangled atoms and lattices as extended clusters. By isolating pairs, we can focus on the simplest units for quantum logic. The swapping process is a way of creating logical connections among data, crucial in any computer. A logic operation is the equivalent of an if-then statement, such as if two qubits have opposite states, then they should exchange values. The logical connections in quantum computers are created using entanglement, which in effect allows for multiple simultaneous correlated possibilities. The NIST experiment was performed with about 60,000 rubidium atoms in Bose-Einstein condensate BEC, a special state of matter in which all atoms are in the same quantum state. They were trapped within a three-dimensional grid of light formed by three pairs of infrared laser beams. The lasers were arranged to create two horizontal lattices overlapping like two mesh screens, once twice as fine as the other in one dimension. This created many pairs of energy wells for trapping atoms. The scientists attempted to place a single atom in each well with one atom spin up, or 1, and the other 1, or down, 0. Then they merged all double wells to force each pair of atoms into the same well, where they could interact with each other. They do that with animals. To create babies at the zoo. I don't know. It's funny. I don't know. It just came to mind. And maybe that's the way you get it to work in a computer. You never know, right? Study the polar bears or monkeys or whatever you want to do. When two such identical atoms are forced into the same physical location, quantum mechanics imposes a specific type of symmetry. Only two of four seemingly possible combinations of quantum states are allowed. Due to this restriction, the merged atoms oscillate between the condition in which one atom is 1 and the other is 0 is the opposite condition. This behavior is unique to identical particles. As they swap spins, the atoms pass in and out of entanglement at the half swap points. The spin of each atom is uncertain, and if measured might turn out to be either up or down. But whatever the result, a measurement on the other atom equally uncertain before the measurement would be sure to be the opposite. This entanglement is the key feature that enables quantum computation. Okay, so the current setup is not directly scalable. I'm just skipping over because I'm running out of battery. Researchers are developing ways to address and manipulate any pair of atoms in the lattice, which should allow for scalable architectures. Not all of the atoms participated.